Okay, this is going to be notes for section 2.3, which is continuity. In your notes, 2.3 starts on the bottom of page 8, and these learning objectives are there, so I'll let you read through those on your own. And then over on page 9 is where we start talking about continuity at a point. Okay? And we start with example 1. But before that, in your notes, it mentions that a continuous function is a function where you can sketch the graph without lifting your pencil. So, right, that would be a continuous function. All polynomial functions, by the way, are continuous, right? All lines are going to be continuous. So those are just some examples. All right, so example 1 says, find the point at which the function f, which we have a picture of here from section 2.1, is continuous, and the points where it's discontinuous. So let's just look at the graph. We can definitely see a discontinuity here at 1. We see a discontinuity here because we have a hole, and then we have f of 2 equals 2 here. And then it looks like from here on we're continuous. So this would be the areas where we're continuous. From 0 to 1, we're continuous. From 1 to 2, we're continuous. And from 2 to 4. So here it is written just the two different ways. So as we go through this video, the nice thing is you can pause it and fill in your notes and then start the video again. So just like we talked about when we looked at the picture, this is where we are not continuous. At x equals 1 and x equals 2 is where we would be not continuous. And then also if you think about less than 0, so this is x less than 0, over here our function isn't even defined, and greater than 4 our function isn't defined. So we could say we're also not continuous outside of those points. Okay, and then we go on to elaborate the definition of continuity to talk about interior points and endpoints. So at an interior point, if you have a function, we say it's continuous at a specific point if this is true. The limit as you approach that point of f of x equals f of c. So an example of this would be like a polynomial. So if you're approaching 4 of, say, x squared minus 6, then the limit here would be 16 minus 6, right? That would be 10. So that would be f of c. If we just plug 4 into the function, that's f of c, right? f of c equals 10. So this we already knew, right? We knew that. We're continuous if when we plug a point in, when we put an input in, we get an output out. And then at the endpoints, we look at just approaching the endpoints from either side. So I'm going to flip back quick here to this function. Because if you look at 0, x equals 0 is an endpoint. So if I am approaching 0 from the positive side, I get a limit of 1. So I would say that's an endpoint because I have nothing happening as I'm approaching it from the negative side. And then for this endpoint on the right, if I'm approaching it from the left side, so this way, then I have a limit. The limit is 1. But I don't have anything from the right-hand side. So that's what this is saying right here. If I'm approaching it from the right-hand side, so in our example, this would be like our x equals 4 endpoint. And if I'm approaching from the left-hand side, this would be like that x equals 0 endpoint. So that previous example kind of shows you what they're talking about for continuity at an endpoint. And if you think about it, x equals 4 and x equals 0, the graph or the function doesn't continue, right? It stops. So those are the endpoints, because it stops there. So if a function is not continuous at a point, then we say that f is discontinuous, and the point of discontinuity is where it's discontinuous. So again, in that example 1, our points of discontinuity were x equals 1 and x equals 2. Okay, then in your graph or in your notes, we have a section where they kind of talk about an example and a non-example. So an example would be something like that. A non-example would be something like this. Notice I had to pick up my pencil to draw this example. So this would be continuous, and this would be not continuous. Another not continuous would be these, right? This one would be not continuous. We have a vertical asymptote, and I had to lift up my graph there. So lots of examples of not continuous. The next example in your notes is a U-try, and they're talking about f of x equals the absolute value of x. Is it continuous at x equals 0? And prove using the definition. So when you prove this one, go back to the definition and look at the limits that you have to show in order to prove that it is continuous at x equals 2. And it is continuous, it is continuous at x equals 0, so that's what you're showing. I'm going to switch pens here because I just noticed this one's bleeding through. Okay, so then the next example that we're going to do together is looking at the continuity of the greatest integer function. Now be careful. This one is not, it's a little different than the one we have been looking at. This one is written, this one is written this way, not that little line shouldn't be there. And on Desmos, it would be called the ceiling function. So this one we're rounding up. The other one that we have looked at quite a bit is this one, which we called the floor. And this one we were rounding down. So this one is the ceiling, so that's why the top of the bracket is filled in, and we're rounding up. So if you look at the graph, these by the way should be open circles. If you look at the graph, when I'm at x equals, say, 1/2, y equals 1. So my table of values looks a little bit like this. If x is between 0 and 1, so any of these fractions, then my output is 1. And then if x is between 1 and 2, my output is 2. So I'm going to the next highest integer instead of going down. So this one is discontinuous at the integer. Because when I'm at, let's look at 1, when I'm at 1, I jump up to here. So here I have a discontinuity right here at x equals 1, a discontinuity at x equals 2, a discontinuity at x equals 3, a discontinuity at x equals -1. So I'm discontinuous at every integer, right? So this is like -2, -1, 0, 1, 2, on and on. I'm continuous everywhere else. So points of continuity and discontinuity would be right there. Okay, now we're going to talk about types of discontinuity. So the first one is a hole. This function is an example of where you have a hole. And you remember when we did this in Algebra 2 and in Advanced Math, when we cancel those out, then we say we have a hole there. It's not an asymptote if you have that same factor at the top and at the bottom. So the first type is removable. And the reason, if you think about it logically, the reason we call it removable is if I can fill in a value here for this hole, then I'm now continuous. The next one is jump. But if you think about step functions and greatest integer and least integer functions, right? If I'm doing something like this, I can't remove that incontinuity or that discontinuity. I can't just fill it in like I could up here. So jump is the second one. Infinity is where you have a vertical asymptote. So this would be an example of an infinite function. And once again, I want you to pause the video and fill these in. So an infinite discontinuity might look like that. And that's not removable, right? There isn't a way to easily fill that in. And then the last one is oscillating. When we did that limits lab at the very beginning of chapter 2, we looked at a few of those limits labs. One of them is, an example, is sine of x over x. It's kind of hard to see on this picture, but this might be a better way to graph this. Starts oscillating right around that 0 there. And we looked at some other ones that did something like this, right? They oscillated here, and then they got smaller as you went out. So oscillating are also not removable. So the only removable type of discontinuity is a hole. So 4 types: removable, jump, infinite, and oscillating. And you will look at problems where you're asked to say what type of discontinuity you have. Okay, continuous functions. So this is the definition. If and only if, remember that means it needs to be true in both directions. So a function is continuous if and only if it is continuous at every point on a given interval or domain. So this is important. And this is also in your notes. So in your notes I might highlight or underline this note word here. So it says a continuous function does not need to be continuous on every interval. So for example, 1 over x is not continuous at x equals 0, right? That's 1 over x. And we have a horizontal asymptote at x equals 0. But that is a domain restriction. So the domain of this function, right, is x is part of all real numbers. So remember, the domain would look like this, union 0 and infinity. In the domain, we restrict it, so we say x cannot equal 0. We would call that a point of discontinuity. But because this is restricted from the domain, we don't include x equals 0, we would still say this function is continuous on the given domain, because the domain doesn't include x equals 0. And it is a good idea to go back in the book and read on page 81 the paragraph under example 3 and read that carefully. See if you can understand that. Next in your notes you have a U-try. It says determine where the function is not continuous. This definitely would be a non-calculator problem. And then say what type of discontinuity it is. So we'll have you do that one on your own, and then we can discuss it in class if you have questions. The next one is properties of continuous functions, and these are pretty self-explanatory. So if you have 2 continuous functions at a point, right, they're continuous at C, then the following combinations are also continuous at C. So addition, subtraction, multiplication, multiplying by a constant, and division. Right, so this would be example of the sum property. So an example of the difference property might look like this, and so on. So, right, if this function is continuous at a point, say x equals 2, and this function is continuous at a point x equals 2, which they both are, because this is a polynomial, and this is a line. I don't know what happened to my light here. There we go. So if I add 2 continuous functions, the sum will also be a continuous function. This same type of idea is true when we are composing functions, right? When we're putting one function inside the other function. So if f is continuous and g is continuous, and you compose f inside of g, then this new function, the composition, will also be continuous. Okay? I'm actually not going to look at that. We'll look at example 3 that's in your notes to show how this works. So this is example 3. So this is a composition of actually many functions. So let's let f of x equal the absolute value of x, so that's kind of like the outside here, and let g of x equal the inside. So then this would be f of g of x. G of x is inside the absolute value function. Now if we look at g of x, let's look at g of x in pieces also, right? G of x is this function, y equals x, which is a line, which is continuous. Sine of x, right, that looks like this. We know that's continuous. X squared, that's a parabola. That function is continuous. And y equals x is continuous. So each part is continuous, right? These are the parts. X, sine of x, x squared, and x. And we have product, we have quotient, we have addition, we have a lot of the properties going on here. So each part is continuous, so by all the properties, I know the entire function g of x is continuous. And then if I put g of x inside f of x, absolute value function is continuous, right? That looks like this, and you just proved it in your U-try that that's continuous. So I'm putting this continuous function inside of another continuous function, so the entire f of g of x also has to be continuous. So if you have to show that a composition is continuous, you have to show that the inside function and the outside function are continuous, and then you know that the composition is continuous. Okay, intermediate value theorem. This is often abbreviated as IVT. And it's well-known abbreviation, so this is an abbreviation you could use on your AP test also. So the theorem is pretty straightforward when you picture a continuous function. It says if you have a function that is continuous on a closed interval, right, a, b, this is closed, so this function is continuous here, and it says if you pick a point between a and b, then the function will also be continuous at that point. So a function is continuous on the closed interval ab, takes on every value between f of a and f of b. So it says any point between here, it's also going to have a corresponding f value that's continuous there. Now this theorem fails if you have even a single point of discontinuity. And don't forget, your closed interval would need to be defined. Okay? Alright, so the example 4 kind of takes this into a different level, if you want to think about it that way. They ask the question, is there a real number that is exactly 1 less than its cube? So is there a number, I don't know what it is, x, that is exactly 1 less than its cube? So this is kind of what we're talking about. So what they're asking is there a number on an interval of a function where if I put in x, this is my input, I'm going to get x to the third minus 1 is my output. So what you can think about doing is graphing this function, right? This is y equals x, and graphing this, y equals x to the third minus 1, and the point we're looking for is right here. It's the intersection point of those two functions. So yes, it does exist, and it's actually equal to 1.325. And while I'm looking at this, I think you could also graph this. So I just took this function and minused x from both sides, and look at the zeros, or the solutions. Right, if I set it equal to 0, I'd be looking at where it crosses the x-axis. I didn't try this, but I'm just thinking this would also get you to the same answer. Okay, so intermediate value theorem, both of these are continuous, and they have a point in the middle of, they didn't give me an interval, but if they gave me an interval, then I'm also continuous at the point in the middle of the interval. And I think that's it. The last thing is we're looking at a homework problem, homework number 25. So they give us this function, and then they say give the formula for the extended function that is continuous at the indicated point. Well, the first thing I notice about this function is I would have a vertical asymptote at x equals -3, right? So when I initially look at it, I think, oh, I'm not continuous at x equals -3. It's my first instinct. But I also notice my numerator factors into this, right? These are perfect squares. X squared is a perfect square. 9 is a perfect square. When I have a minus in the middle, I can factor that way. And then I have x minus 3 at the bottom. X minus 3 and x plus 3 and x plus 3 divide to give me 1, and I'm left with this. So this is actually not a vertical asymptote. This is a hole at x equals -3, right? And when I simplify, I get this extended function y equals x minus 3. So this is the extended function that would be continuous at x equals -3, because this function at -3 would be -3 minus 3. That would be -6. Okay, so when you're looking for discontinuities, you want to simplify first and determine if you actually do have a vertical asymptote or if you have a hole. In this case, we had a hole. So that's why this is a removable discontinuity, because it's a hole. And actually, it's really just a line. If you put this in your graphing calculator and this in your graphing calculator, you will get a line for both of these. So that is it for 2-3. Page 13 in your notes. That's gonna be something we do in class. So that's it for 2-3, short section. Okay, we'll talk about the homework assignment in class. Thank you.